An astronaut steps into sunlight, then instant black shade. One boot bakes, the other nearly deep freezes. That temperature trap is only the beginning. The moon attacks with dust, silence, darkness, distance, and delay. And the worst surprise may feel almost ordinary. Picture gray powder creeping inside a spacesuit zipper. It looks soft, almost harmless, like fireplace ash. It is nothing like ash. Moon dust is sharp, angular, and stubborn. There is no rain there to polish it smooth. No rivers roll it into rounded sand. No wind softens its edges over time. So grains can stay jagged for millions of years. Apollo crews learned that almost immediately. Dust scratched visors, clogged seals, and wore moving parts. It stuck in fabric, hinges, gloves, and boots. On Earth, dirt is annoying. On the moon, dirt becomes slow damage. And damage there never stays small for long. The next surprise hides inside the airlock. Astronauts tracked that dust back into the cabin. Once it floated indoors, some noticed a strange smell. Not because outer space has an odor. Vacuum cannot carry smell to human noses. The scent likely appeared after dust met cabin air. Freshly exposed particles reacted and produced a burnt tang. Some compared it to spent fireworks. Others said hot metal after welding. That detail matters more than it sounds. It means contamination followed astronauts back inside. The danger was not only outside on the surface. It rode home on boots, tools, and suit joints. And if dust enters the cabin, where else can it go? Now imagine breathing near those drifting particles. Scientists still study exactly how risky lunar dust could be. But shape alone raises concern. Sharp grains can irritate tissue more than rounded dust. That matters for eyes, skin, and lungs. Apollo crews reported irritation after moonwalks. Not a dramatic movie collapse, something more realistic. Scratchy throats, watery eyes, and persistent grime. On Earth, storms usually move dust away eventually. Inside a lunar habitat, humans must remove every grain themselves. Filters become precious. Cleaning becomes routine. Routine becomes survival. That is the first big lunar lesson. The moon does not always hit hard. It keeps scraping until systems start losing. Now zoom out to the temperature ambush. Most people imagine the moon as simply freezing. That is the myth. Truth is crueler, because the moon lacks thick air. Earth's atmosphere spreads heat and softens extremes. The moon barely has that protection at all. So sunlit ground can get hotter than boiling water. Degrees Celsius is a useful shorthand. Nearby darkness can plunge far below Antarctic winter. Degrees Celsius is possible in shade. Those numbers can sit shockingly close together. A few steps can cross a thermal cliff. On Earth, shade feels gentle. On the moon, shade can become hostile terrain. Even metal tools can swing between punishing temperatures. A handrail in sunlight behaves differently from one in darkness. The landscape looks still. The physics are constantly trying to catch you off guard. That is why a spacesuit is not just clothing. It is a tiny, personal spacecraft. It must reject excess heat in sunlight, then hold warmth inside brutal shadow. It must supply oxygen, remove carbon dioxide, and manage moisture. It must also block radiation and tiny impacts. Every layer solves one problem and complicates another. More protection usually means more bulk. More bulk means stiffer joints. Stiffer joints make ordinary movement expensive. An astronaut is not just exploring. An astronaut is balancing heat, air, pressure, power, and time. Even standing up can cost effort. Even kneeling can become awkward engineering. And that famous lunar bounce hides another truth. Look closely at those bouncing walks. Yes, lunar gravity is lower, but of Earth's changes everything. But low gravity was only part of the story. The suits resisted bending at hips, knees, and shoulders. Backpacks shifted balance. Boots met dust with odd traction. A small hop could work better than a normal stride. That is why motion looked so strange. Not graceful floating, more like careful problem-solving with every step. If you trip on Earth, you usually curse and recover. If you trip on the Moon, life support is involved. A fall can slam equipment into rock. It can damage connectors, crack parts, or waste energy recovering. And getting back up in a pressurized suit is work. The Moon turns clumsiness into mission risk. Then the landscape starts lying too. The horizon there can fool human eyes. From far away, the Moon looks smooth and simple. Up close, it loves optical tricks. With almost no atmosphere, distant features stay very crisp. That sounds helpful, but your brain expects haze. On Earth, hazy distance helps judge scale. On the Moon, crisp edges can make objects seem closer. A crater rim may look nearby and still require a long walk. A slope can appear gentle and feel much steeper. Apollo astronauts mentioned trouble judging distance and depth. There were fewer familiar cues: no trees bending in wind, no blue sky behind hills, no moisture softening contrast, just bright sunlight, black sky, and hard geometry. That visual confusion sounds small until navigation depends on it. And navigation gets worse the moment sunlight disappears. Darkness on the Moon is not normal nighttime. Earth nights still glow. Air scatters light. Clouds reflect cities, stars, and moonlight. The lunar surface offers no such softness. If sunlight is blocked, shadow can look brutally black. Step behind a boulder, and detail can vanish quickly. 1 second your eyes face blinding brightness. Next second, they face harsh darkness. That jump strains both cameras and people. A hole, cable, or rock edge can hide easily. The Moon is famous for beautiful contrast. That same contrast can become a practical hazard. Bright landscapes create black traps, and black traps become worse because nothing there makes a sound. Space is often described as silent. Outside the suit, that part is true. Sound needs a medium like air or water. The Moon has almost none, so open air carries almost nothing to your ears. No wind across the helmet, no crunching footsteps through the vacuum, no clank from a dropped tool nearby. If a hammer strikes rock, you would not hear it normally. Instead, vibrations can travel through the suit or your hands. That creates an eerie mismatch. Your eyes see impact. Your ears get almost nothing. Humans evolved in noisy environments. We use sound for distance, danger, and reassurance. Remove it, and the brain loses context. The Moon is not just quiet. It subtracts a sense you constantly trust. And silence is only half the communication problem. The other half is delay. An astronaut cannot speak with Earth like a nearby partner. Radio signals need time to travel. The Moon is close by cosmic standards. Human reaction times still care. Seconds one way matters during trouble. Round trip, that becomes about seconds. That delay interrupts instinctive conversation. Ask a question. Wait. Keep working while the answer is still crossing space. In a fast emergency, that lag feels huge. It forces a different mindset. Crews need checklists, discipline, and local decisions. Mission control can help, but not instantly. The Moon teaches autonomy by force. Even perfect voices arrive late. And not every danger announces itself with words anyway. Micrometeoroids are one of the least visible threats. Forget giant flaming movie rocks. Many are tiny fragments moving extremely fast. Earth is protected by a thick atmosphere. Much small debris burns up before reaching the ground. The Moon lacks that shield, so the environment is more exposed. A tiny particle can carry serious energy at high speed. Habitats, visors, and suits must account for that. The chance in any second is low. The consequence can still matter enormously. That is lunar danger again. Often invisible, often statistical, never fully gone. You can walk across calm gray dust while high-speed particles exist overhead. No thunder warns you, no wind shifts, no smell changes. The threat is silent, ordinary-looking, and constant. Then sunlight adds an even harder enemy to picture. Radiation on the moon is harsher than many expect. Earth protects us with both air and magnetism. The moon offers far less shelter. That means solar radiation and cosmic rays matter much more. A short visit is challenging. A long stay becomes a planning puzzle. Habitat walls may need extra shielding. Stored water can help block radiation. Regolith itself may become building material for protection. Storm shelters become more than a science fiction idea. Timing outdoor work matters. Forecasting solar activity matters. A solar particle event can turn a normal day urgent. And unlike earthly storms, there may be no sensory warning, no dark clouds gathering, no pressure change on skin, no smell before rain. Danger can arrive through clear sunlight. That feels deeply unfair. The moon can hurt you with things you cannot see. Now return to the dust, because engineers keep doing that. Lunar dust is not only sharp, it can also be electrostatically troublesome. Sunlight and charging effects can help particles cling. That means brushing a suit clean is harder than expected. Some dust simply does not want to leave. It sticks to fabric, corners, seals, and tool handles. Then every returning astronaut becomes a delivery system. Inside a habitat, each grain becomes maintenance. Filters must catch it. Surfaces must resist it. Air systems must manage it. Cleaning procedures become daily defense, not housekeeping. This is one reason moon bases are harder than posters suggest. The dramatic part is landing. The exhausting part is keeping the place livable afterward. The moon does not stop invading once you enter the door. It waits on every surface, ready to spread. Dust also changes how machines age. Rovers, drills, solar panels, joints, and sample tools all suffer. A grain in the wrong seal can reduce performance. A scratched visor can reduce visibility. A coated radiator can affect heat control. A stiff hinge can waste astronaut energy. None of that looks cinematic. All of it compounds. That is why lunar missions care about tiny design details. Seal shape matters. Coating choice matters. Material wear rates matter. One bad interaction repeated times becomes a mission issue. On Earth, repair crews often improvise with nearby supplies. On the moon, every spare part has mass. Every kilogram launched costs planning and fuel. So small failures become expensive quickly. The moon punishes inefficiency. Then it offers one of its strangest contradictions. The surface looks dry and dead, yet some of the most valuable resources may hide there. Scientists found evidence of water ice in permanently shadowed polar regions. That sounds almost generous. It is not simple generosity. Those shadows are among the coldest places in the solar system. Some measurements suggest temperatures below degrees Celsius. So the useful resource hides inside extreme danger. Ice could support drinking water, breathable oxygen, and rocket fuel. But reaching it means operating in brutal cold and darkness. Machines must work where sunlight barely helps. Power becomes harder. Navigation becomes harder. Human activity becomes harder. The moon hides treasure inside a freezer. That may be its most honest metaphor. Everything useful there seems wrapped in difficulty. And the final surprise may be psychological. Most people imagine the scariest lunar moment as stepping outside. The stranger truth may come later. You return indoors after a moonwalk. Dust follows you. The cabin smells faintly metallic. Your muscles are tired from fighting the suit. Your eyes are adapting after violent contrast. Your brain still expects sound that never came. Conversations with Earth never feel immediate. Equipment already shows scratches from a place with no weather. Then the realization lands. The moon is not dangerous in one dramatic way. It is dangerous in many small ways at once. Friction, delay, glare, contamination, stiffness, exposure, and fatigue stack together. Nothing needs fangs. Nothing needs storms. A sharp grain, a bad angle,